Welcome to Mt Tam Astronomy, a summertime lecture series normally held in Cushing Memorial Amphitheater on Mt Tamalpais, north of San Francisco. I'm Tucker Hyatt, founding director of Wonderfest, the Bay Area beacon of science. Please join me now for another enlightening astronomy program. The age of astrobiology has begun. We have a whole solar system and a galaxy of star-warmed worlds beyond to explore for life. How do we look for life here and way out there? How will we know it when we find it? Our exploration begins at Earth. We must apply what we are learning about our amazing home planet to our search for life beyond. Now, Dr. Penny Boston, former director of NASA's Astrobiology Institute, presents Astrobiology Under Our Feet and Out to the Stars.
Hi everybody, my name is Penny Boston and I am a scientist at NASA Ames Research Center in Moffett Field, California. I was originally scheduled to give this talk to you lovely folks in person before our current pandemic situation, but we decided to go ahead with keeping that engagement and doing it in a pre-recorded fashion. So I have some exciting things that I really want to share with you tonight. The title of my talk is Astrobiology Under Our Feet and Out to the Stars. And that brings together all of the different kinds of work that I've been involved in for many years, along with our aspirations for spaceflight and exploration of other planetary bodies. The real question that astrobiology tackles is, where is there a home for life? Where besides Earth can we find evidence of living processes of some sort? My day job is pretty fabulous, although it has the same amount of paperwork that anybody's day job has. But I get to study some of the most extreme cave environments on this planet, and I get to think about how to find life on other planets. I think about how humans will explore the moon and Mars, and perhaps someday beyond. And I wonder if we can, or even should, permanently transplant Earth life to somewhere like Mars. Astrobiology is a term that was really created about 20-something years ago. Originally, it was called exobiology, meaning biology beyond Earth. In the mid-1990s, we reshaped this to be much more encompassing of everything from how solar systems come together and are formed, how the chemistry that goes into making up life is actually created in the universe, and how all of that comes together through evolution of life with its planet of origin and perhaps beyond. So what is it? It's a vast field of extremely interdisciplinary interactions between biologists and chemists and physicists and many, many more different types of folks. We study it by looking for examples on Earth of life processes that might fit the environments of other planets. And we study it because we have a fundamental interest in the origin of life, in our place in the universe, and if we're alone or if we have companions, albeit very distant companions, on other planets in our solar system, or even other planets in the greater galaxy and beyond. So the folks who study it, as I say, are all over the map in terms of how trained they are. Everything from scientists and engineers to sociologists and linguists and artists and musicians. Astrobiology tackles a number of different scientific topics life in the universe, particularly, of course, the physical precursors to that life, how planets are formed, the chemistry that occurred in order to give rise to the very earliest forms of proto-life or pre-life, the development of that life as we experienced it on Earth, and we can see it in the rock record that we have here. How does life persist in spite of the fact that we know that our planet has been through many, many different epochs that were much more hostile to life at intervals than other times? What is the probability that life will occur on any given planet in any given system? And what is the ultimate fate of that life in a solar system? And where is it? Where do we look for it? This causes us to dig into the very fundamental essence of the nature of life. Most of us who work in this field, and philosophers of science and others who are interested, have our own operational definition. And I say operational because it's very difficult to nail down exactly what life is. It has a whole spectrum of different properties, but no single property is enough by itself to actually show that something is alive. We think about alternative chemistries. Could other life be made in a very different way than we're made here on our planet? What is the nature of intelligence, and how does intelligence arise? Are we the first creatures to rise to the level of intelligence that we possess? Or has this happened before in the history of our planet and we just don't know about it? And what about intelligence elsewhere in the galaxy? Some very science fiction-y concepts have even been advanced and explored in a rigorous scientific way, as well as we can do, considering we don't have any examples of this. And this consists of the idea of energy rather than matter maybe existing in some lifelike form. We don't know, but it's important to keep our imaginations open. And so one of the most critical things to think about when we're trying to shape how we go about doing the tasks that we have is to realize that it's very, very difficult. We're trying to almost write a field guide to unknown organisms that we don't even know exist. And we do that by studying the extreme environments on Earth and who lives there and how they make a living, and by studying the fundamental properties of Earth life, and then studying other planets that we have in our own solar system. And increasingly, we're beginning to get glimpses of planets around other suns. And we try to put all of this scientific knowledge and speculation and inference together to try to develop ideas about how to look for potential life that may be out there. Astrobiology is so interdisciplinary that it's really nested, as you can see in this slide, right in the middle of engineering. We need a huge amount of engineering to actually do the work of sending missions to other planets to look for life. It's nested within astronomy because of the emphasis on the planets that are homes for life, and the extreme environments that I mentioned before, but also this entire spectrum of other disciplines in science and engineering. And so all of that comes together to enable us to tackle these topics. Why is life hard to find? Why haven't we found it yet? Well, probably because it's not likely to look like this science fiction creature that I show in the slide here. I've always wanted to get in my galaxy hopping vehicle ever since I was a little kid and bop around the universe and try to find things with tentacles and weird appendages and amazing animal-like creatures and so forth. But the truth is that on our planet, 3/4 of the history of life on our planet has been microbial, strictly microbial. It was only in the last quarter of the history of Earth's life that we have had larger creatures. And so that means that the probability of microbial life being the most likely thing that we will find, certainly in our own solar system, is very high. If you are an organism and you are made of yummy stuff, then you are a packet of goodies for other organisms to take. And so there's a high premium on being cryptic, that is hiding. So that is another factor. And life may be very, very different from us. It may be very different in terms of chemistry, in terms of its biological, fundamental molecular structure. Even the size scale may be different. We have rules of thumb on Earth where we are knowledgeable about organisms of different sizes. We say, oh, bacteria are maybe in the 1 micrometer range. Maybe fungi are in the 10 to 50 micrometer range. Viruses are just maybe 50 nanometers or in that range. And so we have these rules of thumb on Earth, but this may be very different on other planets, and we don't know that. So we have to be wary and keep our eyes open for that. The speed of activity of life could be very, very fast. It could be very, very slow. We have examples of both of those here on our planet. And so we also have to be aware of that variable. And the location of life on another planet could be radically different. So for example, in the case of Mars, or under the ice sheet in the oceans on Europa, a moon of Jupiter, it could be that all of the life on those bodies is in the subsurface rather than on the surface. So we are guided by our limited experience, and part of our job is to expand that experience. How did I personally wind up in big holes in the ground? I was not a recreational caver. I got into the whole issue of going into Earth's subsurface really as a byproduct of the fact that I was an astrobiologist, exobiologist, geomicrobiologist. And the other factor really is that there are too many sciences that appealed to me. So when I was young, I was told, well, you know, you've got to stick to one thing, otherwise people won't take you seriously. Well, the secret is that astrobiology is the perfect place for people who love more than one science, because this is a place where all of those sciences come together. And then, of course, I grew up in the late 50s and the 60s, and this was a time where geopolitically we were influenced by competition on all levels of life with the Soviet Union, and the shock that went through the United States when the Russians launched the first satellite that was known as Sputnik actually spurred our government to really put a lot of emphasis in training in science, math, what we now call STEM disciplines, engineering, and this was a revolution really in education, and I'm one of the many folks who benefited from that when I was young. So caves, why do we care about caves? Besides the astrobiology, there are a lot of other reasons. Lots of people love to explore caves. Caves give you a unique view on the geology of the rock units and the geographical areas in which they occur around the world. They're actually windows into the subsurface where we can see much more about the hydrology, that is the movement of water, the storage of water. We can see all sorts of mineralogical phenomena that occur. And so this is a wonderful place to apply your trade if you're an earth scientist. Of course, cave biology and microbiology are where a lot of my efforts have revolved around. Many other colleagues who study everything from cave fish to tiny microbes, and astrobiology, as I've mentioned, but also paleontology, that is the remains of animals and plants from prior epochs are beautifully stored in caves, and the same is true for human remains and artifacts, and that brings in archaeology. One of the great awakenings really in human understanding as we have grown more and more to realize that we need to be stewards of our planet is really the stewardship of caves as precious wilderness environments, and how to meld access to these features for recreational purposes for the public. I often joke that it's also an unparalleled opportunity to look glamorous at all times, and this slide shows a potpourri of me in all different kinds of gear. The reason that we're all dressed up like this is because typically, because we're looking for extreme environments for microorganisms, we are in caves with extreme chemical and sometimes extreme temperature conditions. So we don't just dress up in goofy suits for fun. It actually has a purpose. So what is a cave? You know, if you think about it from the person's point of view, it's really a big hole in the ground into which people can enter and get. This is sort of the average caver's view of it, and it's one of the blessings of being able to get into caves is that we can access places that otherwise we would not be able to easily access. But if you're a much smaller creature like a salamander or some other small thing like a small invertebrate, then it's really a hole in the ground that's big enough to provide habitat of some sort. If you're a microbe, your needs are even smaller, both physically and in terms of what you need. So even pore spaces in sandstones and things of that sort can provide habitat space and interconnections so that fluids and gases and even the microbes themselves can actually travel between those tiny spaces. One of the critical things to understand is that we have at least 300,000 known caves in the world, but that is a very small proportion, and of the caves that actually exist, most of which do not have natural entrances. So they are big or small or medium or tiny cavities underneath the surface of the ground, and they are caves that you only discover if you happen to accidentally dig into them. Sometimes this happens in the process of mining activities. Sometimes it happens in the process of road building or some other kinds of excavation. And so what this shows is that the subsurface world of caves on Earth is really quite a vast area of wilderness. So cave environments themselves are quite different from the surface. They are dark, no surprise, and that's beyond the twilight zone. So the twilight zone in a cave is where you have at least some of the outside light coming in. The image here shows Lechuguilla Cave in New Mexico, the entrance drop, and you can see rain coming in there while the sun is shining. It's a beautiful image. And so rapidly, though, you get out of the zone where photons, where light can actually penetrate. Caves, because they are restricted from the surface or even totally closed to the surface, tend to be closer to the water table. And so therefore they often, in most cases, have very, very high humidities, approaching 99 to 100%. So they're very soggy environments, even if the overlying environment is not. The temperatures within any given cave are fairly constant. They don't vary very much within the cave, but you can have caves of all different temperatures depending on where in the world you are. Food is a problem if you're an organism living in a cave, because we live on a planet where a lot of the biosphere is driven by photosynthesis, and that is the surface process that captures sunlight by plants and photosynthetic microorganisms, and they turn that into more biomass. And so when you put that together, of course, on the surface, you have all that delicious material to take advantage of. But in a cave, you get a limited amount of that coming into the cave, but you can make your living on other things. And so the microorganisms that we're particularly interested in are the ones that don't eat organic material like you and I do. They eat minerals, they eat rocks, and so they get their energy from inorganic materials. Because there's no surface weather in the cave environment, this means that they are wonderful preservation environments. So this is one of my favorite examples on this slide of cave environments. The background picture that you can see is the Rub al Khali, the empty quarter that crosses Saudi Arabia, Yemen, Oman, and the United Arab Emirates. And this is a very dry sand dune desert. But within this desert, there are many caves, and you can see the figure on the left. One of the cave scientists is looking into a small hole. And if you actually go into a lot of these holes, you are in a totally transformed world. If you can see the image on the lower right, you can see someone diving a pool, and this is in one of these environments. And so you can see that the very dry desert environment on the surface, even with a cave with an opening in it, you are transformed as you go across that boundary from the surface into the cave into a totally different world where very different organisms live, very different chemistry is occurring, and it's an entirely different world. Caves occur not just in limestone, so I'm sure a lot of you folks have visited show caves, and most of them are in limestone rock. And this is because we have a lot of limestone on Earth and we have a lot of water. And so the limestone is dissolved in several different ways, but there are many other ways to make holes in rock of all different kinds. So this photograph composite here shows many of those. The lava tubes that are a byproduct of volcanic activity. There are caves in granite that are produced by the exfoliation of rock layers, by decompression of the rock masses. There are quartzite caves, where quartzite is a very non-soluble rock type, but if you give it the right conditions, that can also dissolve out caves. Even in big rock salt areas, like the image on the lower left shows an area in the Atacama Desert in Chile that has caves in halite or rock salt. Caves in marble, shown in the beautiful figure on the center bottom of this composite, shows how beautiful marble caves are on the inside. The lower right shows a gypsum cave. So gypsum is a very soluble mineral. It is calcium sulfate, and in fact it's the material that is used in paints. It's the predominant constituent of wallboard in our houses and buildings, and yet there are massive deposits of this in places in the world where there is the ability for the circumstances to have led to caves. And so we have even those kinds of caves. We even have caves in ice. And so in the Antarctic, particularly in hot spots that are near the active volcano Erebus, we have fumaroles caused by the heat of the volcanic activity, and this melts away part of the ice layer and creates caves. So you can make caves out of almost anything. Just to give you an idea of the size of the features that we're talking about, these are the Whiz facts. The longest limestone cave that we have on Earth that we know about is Mammoth Cave in Kentucky, right here in the United States. It's about 350 miles of passage, and this is measured not in a linear fashion, but this is all of the passages that go all different directions, measured and then added up. The longest cave in gypsum, which is a very soluble mineral, quite remarkably, is well over 150 miles, and this is in Ukraine. Which is famous for very large gypsum caves, has about the 3 or 4 longest gypsum caves in the world. The volcanic caves that I mentioned before, the lava tube caves on Earth, the longest one known and documented is in Hawaii, on the big island of Hawaii, Kazumura Cave, and that's over 50 miles long. There are many caves in the world that are underwater, and these are often created before the area is underwater. So they're the caves that are formed by processes that are partly in water and partly not. But then we have sea level rise and fall over geological time, and so they have been inundated with water. When we think about actually the deepest natural cave, it's Cribera Cave, and it's well over 1.25 miles. and its exploration is still continuing, and so that may go even deeper. The deepest access that we have to the subsurface right now is actually in a human-created cave, also known as a mine, and these are the amazing South African gold mines that go down over 4 kilometers. That's more than 2 miles. And in fact, every time I update this slide, it actually gets a bit longer. So I rounded it to 2+, so I don't have to keep track of it. But it's an amazing thing. And at those depths, of course, the conditions are very, very hot and very, very difficult. And yet, even there are microorganisms living in the fractures and the cavities that contain fluids at that depth. So I want to turn to a brief overview of cave life. The gooey things that you see hanging off the beautiful shining crystals in the back of this slide are an extreme form of bacteria that takes hydrogen sulfide gas in the environment of this particular cave in Mexico and turns it into energy for itself. It manipulates it chemically, and that's what it lives off. And it forms these gooey strings that hang down from the crystals within the cave. The insert, you can see a very typical invertebrate, typical cave invertebrate. It has a lot of adaptations for living in caves. On this slide, you can see the different ways that organisms use caves. So the cluster of ladybugs on the upper left, those guys are just visiting. They very often have these mass swarms, and they visit caves because caves provide shelter from weather conditions. They provide some protection from predators, and they also provide a place for organisms to mass when they're getting ready to think about mating. There are organisms that just make the cave their home base, but they go and scavenge for food or hunt food on the outside, and this includes the cave cricket that you can see in the upper right, with very, very, very long antennae and very, very long legs, so that they can use the sense of touch to navigate through the cave. You can see in the lower right the bat, one of many, many species of bats that use caves as home base. They use caves as nursery environments, and they also, in cold climates, use them as a way to see out the winter. It then becomes what we call a hibernaculum, or a place for winter survival. On the lower left, you can see a very odd looking little fishy, and that fishy is a permanent resident of caves, and is one of the fish that shows a lot of these extreme adaptations that cave animals develop. That is, it's lost its pigmentation, it has no functional eyes, it has very sensitive fins and skin and sensors within its skin, and it is permanently in the cave. It does not leave for any reason. I want to discuss a little bit about adaptation here with my tale of 3 millipedes. So we know that animals on the surface use their color to signal different things or to hide themselves. So the millipede on the left is a bright red, and it's advertising that it's a poisonous creature. And it's saying to predators, don't eat me because you'll get a mouthful of nasty stuff. The millipede in the center is on a very gray, metallic looking rock, and the millipede herself is actually a very shiny gray color. And so she's blending in with this background of her environment. But the one on the right, this millipede on the right, shows those same adaptations that I was just mentioning. She's in the dark, so she doesn't need her pigment, and it costs metabolic energy to make pigment, so she saves energy by not doing that. She has very long antennae compared to other millipedes on the surface, and she also has no functional eyes. So she's a perfect example of how you would develop if you wanted to live in a cave permanently. One of the things that I have to mention is that the subsurface is very precious, but it is one of the least protected of any wilderness types. And this comes from a long history of people not really understanding caves. They've been used to throw sewage and junk, and they have been the targets of, in some cases, massive vandalism. They can collect pollutants that are released on the surface. And this is a very bad thing. Not only do we want to preserve the caves, but caves and groundwater are very often inextricably bound. And that means that in places where we get our potable and drinkable water from the ground, from groundwater, we are potentially seeing the effect of polluting our own water supplies. And so caves have very practical uses and very aspirational and artistic and precious wilderness values as well, and they deserve protection. This image, set of images, shows some of the amazing cave formations that we find. And I'm sure that you're all familiar with the common cave structures that we find called stalactites and stalagmites. As far as we can tell, those are essentially mineral processes. They're chemical processes that are produced. But because of this unique relationship of microorganisms within the subsurface and their ability to gain energy in an environment that doesn't have a lot of what we would consider conventional food, they interact with the minerals in their environment. And so that microbial and mineral interaction produces spectacular structures. You can see one of my cave colleagues on the left is actually sampling what looks like white mud or something of the sort, but this is called moon milk, and this is a product of the activity of microorganisms and the organic acids that they produce as a byproduct of their living processes that actually alters the chemistry and the form of the bedrock into this fluffy mineral. The pool fingers that you can see from Carlsbad Cavern in the upper right, these are pool fingers that grow from a combination of the action of microorganisms and the precipitation of limestone dissolved calcite, the mineral calcite, in combination together. Even what we call cave pearls, which are these exquisite spherical objects that we find loose within what are called cave pearl nests in caves, are a combination of the action of dripping water, just as you would have producing a stalactite or a stalagmite, but it's combined with the physical and chemical properties of microorganisms in the environment to actually produce these unique shapes. I want to talk for just a moment about biominerals, because this is a relatively new insight that has come out of the work of colleagues like Bob Hazen and his team, who first called our attention within the scientific community to the fact that, in Bob's scheme of things, he and his colleagues identified the fact that we have essentially 12 primitive minerals in the early solar system, and we see those well represented in a lot of the small bodies like asteroids and so forth that we have in our solar system. But if we look at Earth, we have at least 4,400 known minerals on Earth today that are described, and their chemical structures are known, and they've all been given names, and new ones are being found all the time. And if you look at the conditions that produce these, that we think produce these, about 1,500 of those 4,400 are due to the presence of the fact that we have liquid water on our planet, and we also have tectonic processes that are always churning our surface material, the crust of our planet, and altering things. But the rest, if you subtract the 1,500 from the 4,400, that almost 3,000 minerals are due to the presence of life, either directly by microbial action or indirectly from alterations in the chemistry of the planet by the life that lives there. We know that there are many minerals that are found only in caves because they have very unique environmental conditions, and some are found in only one cave in the world. So if you're a mineral collector or very, very interested in minerals, caves are your friend. I want to talk now to the organisms that I've been mentioning, this idea of extremophiles. Extremophiles on Earth are organisms that we believe live in an environment that has a lot of challenges. So, trying to decide what an extremophile is, we have to sort out our attitudes towards that, because there are places on Earth that we as humans find very uncomfortable, but the organisms are completely at home. And so what does extremophile really mean? On Earth, life is everywhere, and particularly microbial life. And so if you just cast a glance on these images, you can see that obviously we are covered in microorganisms. They are our friends for the most part. They protect us. They are our partners in the ecosystem that is each one of us. We think of ourselves as individuals, but in biological terms, every one of us is inhabited inside and out through our entire gut and throughout our surface with organisms that cooperate with us, conduct many processes that we need, convert some materials into useful vitamins that we can't make ourselves. And so we are thoroughly microbial ourselves. In fact, we know that only 1/10 of the cells that make us up are actually our own human cells. And they are bigger cells than bacteria, but the bacteria are far more numerous. And so 90% by number of all the cells that are on you and in you and that are you are actually microbial. But we find these microorganisms not just on us, but we find them even in what we at one time would have thought were unlikely places. This is a few examples of the many places. So a methane biofilm on rock in a water environment. Microorganisms are highly involved in metal corrosion. So it's not just a chemical process on Earth. Everywhere you find metal rusting, for example, anything containing iron on Earth has got a microbial component where the microbes are helping that rust take place. We've even found organisms in nuclear plant cooling towers and found organisms that are incredibly resistant to ionizing radiation. There are many organisms that deal with what we would consider toxic metals like arsenic, and you can see that picture there. This is representative of a whole suite of microbes that can actually use these toxic metal containing minerals for energy, or they detoxify them in some way, so they have many ways that they interact with them. We, of course, have to have fresh water in order to supply our needs, but so many of the bacteria that we find and the other type of very small life that are known as archaea actually live in completely hypersaline environments and are perfectly happy. And of course, in the realm of temperature, we have organisms at very cold temperatures, or we have them in places like the deep sea hydrothermal vents, which are very, very hot. So what is an extreme environment? This background image shows myself and two of my longtime caving scientist colleagues in a sulfuric acid cave in Tabasco in Mexico. This is one that we've studied for well over 20 years now. And it is an extreme environment for humans. We can't breathe the air without assistance for the most part. But if you look in there, it's absolutely covered with life. And so for the organisms that live there, it's actually home sweet home. Now that isn't to say that there aren't real challenges even for those organisms. And so this is a very acidic environment in this particular case. So there are real extreme physical and chemical limits to life that make something truly extreme. But one of the things that makes a connection directly to the astrobiology is that the extreme conditions on Earth, as we define them, might be average planetary conditions on other bodies in our solar system and beyond. So that makes a relatively fluid concept of what constitutes extremes. And we look at those in order to try to understand how organisms could make a living on planets where the average conditions are very different from ours. This next slide shows a potpourri of some of the amazing ways that microbes are visible to the naked eye in the cave environments. So individually they're small, but in these environments they very often occur in very large patches that include the microorganisms themselves and things that they are doing to transform the minerals. And so you can see these red patches from Lechuguilla Cave. You can see the Sudan mine features that contain all kinds of organisms that are oxidizing iron compounds because it's a big iron mine. You can see in the upper right hand image all this drippy stuff that I showed you before coming from that acidic cave in Mexico. In the lower left you can see what looks like a stalagmite, a sticky uppy as we call it, very dark in color with a very black cap. And this happens to be organisms that make their living partly off oxidizing manganese materials. And that entire speleothem, as we call it, that entire formation is growing on a miner's jacket. So we know exactly when that miner's jacket was left there because it was when the mine closed in 1962. And so in that period of time, this entire formation has been created by microorganisms working on the minerals. The beautiful blue examples with my colleague standing there for scale, and then the up-close image on the right that shows what looks like a tiny blue stalactite. Those are all the transformations of copper minerals by microorganisms. In this potpourri, you can see once again the colleague who is examining that white fluffy material that I mentioned before, but directly to the right of that you can see all of this red and black and sort of blue-black material. This is all another way that microorganisms use iron to make a living and leave that fingerprint of minerals in a cave environment. The image on the lower right shows what look like silvery white patches, and these are a group of bacteria known as actinobacteria, and these are quite extraordinary creatures. They're very common in our soils. They're very common in caves, and in fact, when you get that beautiful smell from soils as they start to reawaken in spring, that comes in many cases from the compounds that these actinobacteria are giving off. The central two lower images are electron micrographs showing some of the amazing forms of the individual organisms that go into making up some of these formations. So we can see them in their individual form, and then we can also see them with these macroscopically visible deposits. When we talk about conspicuous subsurface life, as we see in this next image, these are all images from lava tube caves around the world. These are provided by different colleagues who have done work in Hawaii, in the Azorean Islands, in Oregon, in New Mexico, in California, and all of those colorful patches are also microorganisms. And so when you look at them, in many cases it's very hard to tell that they're actually live. They look like mineral deposits. But my friend and colleague Diana Northup has coined the term microbes that masquerade as minerals, and this is a perfect example of that capability. One of the other things that microbes can do is organize themselves in space in a way that lets us know that they're there. And we call this biopatterning. This slide shows all different kinds of biopatterning at all different scales. And so all of those wiggly hieroglyphic patterns that you see on the rock walls at different scales are all microbial deposits where the microbes are growing. They're trapping particles from the fluid. They're getting nutrients out of some of those. They're also producing minerals while they're growing. And all of these give us a clue that life is there. And in fact, these patterns can actually fossilize. And so one of the things that we speculated about is if you find a cave on another planet where life may have been present very long ago, who knows what you might find? You might find very ancient representatives of patterns like this that might indicate that you have found a site where organisms might have been active in the past. I want to now turn for a few minutes to the whole issue of extraterrestrial caves, because the connection with astrobiology is that we're studying the caves on Earth, and we're studying the life and the mineralogy of the caves on Earth for their own sake, but also so that we can apply those as templates as we try to figure out how to look for and how to recognize the potential signals of life elsewhere. So what are the prospects for caves on other planets? Well, 25 years ago when I first started writing about this topic, we didn't really have any identified caves on other planets. And so it was a hard sell to convince people that there were probably holes in the ground on these other bodies. But in the intervening time, from a lot of different space missions, we now actually have visual evidence of caves of many different kinds. You can see examples, and I'm not going to slavishly go through this, but examples from the moon, these big giant pits. We have lava tubes on the moon. We have big giant pits on Mars. We have lava tubes on Mars. Even on the planet Mercury, which is an incredibly hot and very inhospitable environment where we don't expect to find life, but we still have cave-like structures that we can see. Even Venus, which is an incredibly overheated planet, may have had life on it at one time, probably doesn't now. We see evidences of lava tubes, these volcanic cave structures. Even on the volcanically active body Io, which is the most volcanically active body currently in the solar system, even outstripping Earth, it is a moon that circles around the planet Jupiter. And even there, we see the active formation of these types of caves. And so those types of caves are quite common, we think, in the solar system. This image shows a lava bridge comparison, and a lava bridge is what's left when you have a lava tube, but a lot of it has collapsed over time. And you can see in the lower right-hand corner, you can see an example from the El Malpais National Monument in New Mexico. And you can see the size scale on there. In the upper left, you can see a very similar example from Mars. And but what you'll notice is that the size scale is very different. And these features on Mars, all of the volcanic features on Mars, tend to be immensely greater than they are on Earth. This is true of the giant volcanoes on Mars, and it's true of the very large lava tubes and pits. And so this is a comparison that shows very similar morphology or shapes, and yet a very different size scale. Turning to an earthly example to illustrate how these kinds of lava tubes are formed, this is an active lava tube forming on the very active volcano Mount Etna. And this was about 10 or 12 years ago that this image was taken. You can see the molten lava visible through a hole in the lava tube known as a skylight. And you can see the flowing of this lava. When the eruption stops, this lava flows out, but it leaves behind it this corridor within the lava, and that is the primary way that lava tubes are made. I want to show you one of the up-close images of a Martian cave entrance. This is a big, beautiful pit. This hole is over 100 meters across. That's on the order of about 300 feet. And the resolution on this beautiful high-rise data that we have been collecting for many, many years now, 30 centimeter resolution, which is about this. And so you can see very, very detailed features of these kind of structures. I compare it here. I compare it here to an American football field. This hole in the ground on Mars is significantly bigger than that. And plenty of room around the edges. And this is very typical of these structures on Mars. We have non-volcanic caves on Mars as well. This is an example of a giant gash that looks like it was perhaps a hole in an ice sheet, an ancient ice sheet that was formed over some volcanic terrain. The ice sheet gathered solid material on it. Dust storms circulate huge amounts of material in the atmosphere of Mars on a regular basis, and then presumably the ice sublimed away or melted away, and then we have this giant gash to someday explore. So I want to think about now what kind of life might live in extraterrestrial caves. This is a fanciful illustration that I did to amuse myself, thinking about whether or not you could actually have some kind of life that actually was based on some sort of biocrystalline structure. We certainly know that in organisms on Earth, we have many crystals. Proteins make crystals. In fact, you could imagine our bones as vertebrates. We have crystalline structures within those. And so it's a subject of speculation how that might develop into an entirely different life form. But getting down to the actual evidence that we have in hand that can allow us to try to infer what we might find, it's unclear how we actually go about it. But we know from our work in the field that we have to interrogate, that is, we have to look at very different size scales. So the one image, you see all of these people in little orange suits amidst a forest of gigantic crystals. This is the Nika system in Chihuahua in Mexico. And so this is a wonderland for microbiology. It doesn't look at that scale. But if we look at a hand scale, you can see the finger in the image in the lower left. You can see this complex three-dimensional raised feature on that surface. That looked to us very potentially biological. And then when we were able to do both light microscopy and at even higher resolution electron microscopy, you can see all of those thread-like structures that are sticking out from that orange wall. It's not orange in the micrograph because there's no true color in micrographs. But you can see all of those structures, and those are living organisms that are essentially partially buried in the clay on the wall and actually having a very happy life, kind of diving in and out of that material. And so when you look back at that large image, you see that even the walls are alive there. And you would not know that if you did not follow this trend through. So who are those kinds of organisms? Well, a lot of them, as I mentioned before, are rock eaters. These are some images taken with either fluorescent dyes and light microscopy in the green background images that you see, and the black and white are once again electron microscope images, and you can see that these organisms are all different forms. These guys make their way through the rock. They mine materials out of it for their own use, and they loosen up the structure of the rock and they turn it into mushy material, and so they are actively degrading it. And they are also then liberating materials within that rock that can be used by other microorganisms. And so it's an entire little community on a very tiny scale, but with a lot of the complexity that you would see in a big surface environment like the Amazon, for example, the jungles in the Amazon. Very often the microorganisms, make very distinctive crystals. Mineral crystals as a byproduct of their activity, and this composite shows beautiful little stars on the lower left. These are we found these made out of iron and sulfur and copper and manganese and other things, and they're a byproduct of the fact that the microorganisms are manipulating the chemistry of their environment. Geomicrobes in lava tubes, as I showed before, produce all different kinds of patches of color. Here are another spectrum that shows this. And when you look at the upper left image, you can see that is composed of lots of little fuzzy blobs, and that's an electron microscope image that shows what the bacteria like that are producing a lot of these. They're beautiful little complex shapes. They grow in vast profusion, and when you look at them with the naked eye, you don't see the individuals, but you see these traces of their existence. We have many mysteries that we already understand on Earth, and this is one of them that I want to show you. We have found these mesh stocking-like structures in caves of all different descriptions, all different temperatures, and all different rock types, and all different geochemistries around the world. We do not know what they are. We have been looking at them for more than 20 years. We have been trying to grow them. And on this slide, it's really pointing out that we are looking in extreme environments, even on Earth, with sensitive biology that we could almost consider alien. It's so different from what we have seen, and we still don't know what they are. So this is good practice for thinking about looking for real alien microorganisms on other planets. I want to turn now to my last few slides and think about the astrobiology missions that we're contemplating to other worlds. Mars is a long sought target. We have had many missions, both from NASA and the European Space Agency, and coming up soon, other countries like India, China, the United Arab Republic are all going to be sending missions to Mars. And so we have this long history with Mars and a huge investment in looking for traces of life and traces of past life on that planet. So that is vigorously underway. In the late 1970s and early 1980s, our early ventures to the outer solar system showed us that a lot of the icy moons that we thought were just inert, kind of boring icy lumps that circle around the planets Jupiter and Saturn are actually extremely complicated, geologically active bodies in their own right, and we discovered that they actually have interior oceans. And so, do those oceans contain life? Have they given rise to life? So those kinds of bodies have become extremely important, and many missions are under study. One mission is going to go to Europa around Jupiter to actually try to see what it can detect from an orbital mission. Someday we'll be sending landers, and same to the tiny moon Enceladus that circles around Saturn, this beautiful little white object that you see in this array of planets. And also Titan, which is a very bizarre object, ultra cold, and where the liquid on the surface are hydrocarbons, and where water only occurs as bedrock. It only occurs in very dense ice forms. We're also curious, of course, about the ancient history of Venus and whether life ever arose there and persisted for some period of time before conditions on Venus became difficult like they now are. And even Pluto, which turned out to be such a fascinating, complicated body. Are there lifelike processes or prebiotic, pre-life processes that we can identify someday on that body way, way out in our solar system? So we know that life's out there somewhere, but as my cat friend here is saying, yes, Dr. Boston, but is it life as we know it? And that is a major question. How do we shape the missions that we want to send? So just in the last few moments here, I want to run through a couple of slides just to give you some more eye candy of some of the environments that we have studied. This is a beautiful example of what we call the chandeliers, these gorgeous calcium sulfate formations that hang down in one of the rooms in Lechuguilla Cave. Lechuguilla Cave is an immense cave, and it contains an enormous number of microorganisms that are doing all kinds of transformations, far more than I can tell you in this few remaining seconds that I have. Extensive microbial activity has probably helped create this cave, and it has helped certainly shape a lot of the beautiful mineralogy that we find there. So those have been under study by ourselves and a number of other colleagues for many decades now. Is that material alive? Well, sometimes it's very hard to tell. It took us years to look at this orange fluff that you can see in this image and determine that yes, indeed, it was not only containing microorganisms, but that it itself, this fluffy iron and manganese material, was actually a byproduct of their activity. Iron and manganese fluff occurs in all different types, in all different caves. I just flashed this up so that you can see the beautiful array of different environments in which it occurs. The series of 3 images down through the center of your screen actually are electron micrographs that show the amazing shapes that some of these organisms and their associated crystals take. The sulfuric acid cave that I mentioned before, it's because it has the availability of the hydrogen sulfide gas. That is the engine, not sunlight. That is the engine for the biological activity in this extraordinary environment. And so one might imagine the presence of such gases perhaps being emitted on the bottom of some of those oceans in the icy moons that I mentioned before. This would be a way to chemically understand how a biosystem could actually exist in those kinds of ocean interior environments that have never seen and never will see the sun. This image that I showed before when I first was shown it, examples from this cave in Chihuahua in Mexico, I thought it was a Photoshop hoax. And you know, because cavers can be jokey kind of people, and I thought, oh yeah, it's a joke. But it turned out to be real, and we have studied it. Not easy to study. It's an exceedingly hot system, and yet what I showed you before and what I'm showing you here, all these thread-like microorganisms sticking out of the walls. There are both live organisms that can be regrown, even from holes, little pockets within the giant crystals themselves. So it's a wonderland. So there are many things for us to look for. We're still at the beginning of this great human adventure. In astrobiology, we think of it not in terms of necessarily our own lifetimes, but really think of it as a multi-generational enterprise that is going to go on long beyond the lifetimes of those of us who are senior, even beyond the lifetimes of those who are very new to the field, our students and graduate students, and even the children who are studying things in school now. So it is a vast, complex way to understand the life in our universe and where it is, and we're tremendously excited about it. In my heart of hearts, what I secretly hope we find is something like Baby Yoda, but I'm willing to settle for tiny microorganisms or even geological remains that look like the activities of microorganisms in the past. So with that, I will close and thank you very much and wish you all well and take care in this era of the COVID pandemic.
I hope you enjoyed watching Astrobiology Under Our Feet and Out to the Stars with Dr. Penny Boston of NASA Ames Research Center. These programs are produced by Mt Tam Astronomy in collaboration with the Friends of Mt Tam, with the San Francisco Amateur Astronomers, and with Wonderfest, the Bay Area beacon of science. The programs are free and open to all. Mt Tam Astronomy is organized by Tinka Ross, and this video was produced by John Navas. To attend a live program, followed by live telescope viewing of the night sky, or for a list of upcoming Astronomy Nights programs, visit our website at mounttamastronomy.org. For Mt Tam Astronomy, I'm Tucker Hyatt.